So thanks, Felix, and organizers and steering committee for giving me the opportunity to talk in front of such a big crowd. I'm amazed. So this is Sunday morning. We all walked outside to come here. It's beautiful, right? You've seen the mountains, yet, I don't know, maybe like 200 of you are here. I think this is a testament not to my tutorial, but to the good health of our field of quantum information. So it's really great to see so many young people here, and I hope you're getting as much as you expect to get out of the tutorials. So I'm going to do my best. Please interrupt me with questions. It's a really wide audience. People here are coming from all sides of computer science, mathematics, and physics. And so it's pretty difficult to be talking to everyone. So please stop me and ask a question. My notation is not clear. It's not even clear what I'm talking about. Then stop me. It's not, I don't have a very strict agenda. We have a lot of time. So it's totally fine to skip some stuff and spend more time explaining a point that's not clear. This is especially difficult given I'm using slides and not the board. But if needed, we could use the board or get into an explanation. I also put, before I forget, so the slides this morning, if I didn't mess up, I put them up at this address. You can just copy, for those of you who have laptops, you can copy the address, or you can find it by going to my webpage, and on the top right, there's like a news kind of thing, and the link is there if you forget about the link. The point is that it could be useful in order to look back or look forward at what I'm up to. And also, one thing is that I haven't been super exhaustive in terms of references. This is a tutorial, a little bit more than a survey. Still, there's a few references, but when I put them, I put like a very short acronym, so it's hard to figure out what the reference exactly is. So the last slide in my slides has a list of all the references. And so if you want to look them up while I'm talking, you can look up the slides online and go to the last slide, and you'll be able to find the papers that are referenced. Okay? Okay, so let's get started. So push down. Yeah, so what's the plan? So I'll spend quite a little bit of time defining what I mean by verification, because there's going to be a pretty specific view on the problem of verification, what we sometimes refer to as a black box verification of quantum computation. So it will take us some time. And I realize when I turn right, you can't hear me anymore, right? So I have to look at you and not at the slides. Okay, the slides are here, so okay. So then I'll give you an overview of approaches to that problem. There's basically 4 of them, so that are listed in the bullets 3 to 6. So after the overview, we'll go into each of them into a little bit more detail, and I'll try to give you some of the ideas. So they use very different ideas that come from different models of computation, that come from cryptography, that come from complexity theory. So I'll present these ideas in each of the settings, trying to connect all of these together. And then at the end, there'll be a little coda, if we have time, where I'll go into a little bit more depth into the main open question in this area and tell you a few things about that open question. So let's get started. What's the problem that we're going to be thinking of for the whole morning? Is this problem. So I'm going to think of a user that's represented here as a puppeteer for good reason. So this user can interact with a quantum machine. So I could call it a quantum computer, but I'm generally going to call it just a quantum device, because it might not be like a full-blown quantum computer. It's just something that can do quantum computations. This user I'll usually refer to as a verifier, and the reason is that the user has a certain quantum computation in mind. That, for example, most of the talk I'll think of that computation as being represented as a quantum circuit that the user would like to evaluate on the machine. So the user doesn't have itself a quantum device, but it has access to that one that's up there in the cloud, such as this IBM computer there. And so the user can interact with the device, specify instructions. The device is going to perform the instructions or not, report certain outcomes. And at the end of the device I'm going to refer to as the prover. The reason is that we'll think of this device as trying to demonstrate to the verifier that the outcome of the circuit is a certain value that the device has in mind, which might not be the actual value, right? So the device might be lying, maybe because it's making errors, or maybe because it's even adversarial. And so at the end of the interaction, the verifier is going to output 2 things. One is a flag, and the other is a bit. So this flag is going to say whether it accepts the interaction or not, so whether it thinks that everything has been going on fine, or whether maybe it detected an error. And then in case the flag says accept, it's also going to return a bit B, which is the bit that the verifier believes is the correct value for the outcome of its computation. And so the goal is the following. We want it to be that if the interaction is such that the probability that the verifier returns acceptance is not negligible, is not too small, then the outcome, the bit B that the verifier declares, conditioned on accepting the interaction, should be distributed roughly as the outcome of that circuit if I were to run it on some default input. Doesn't really matter. Here I chose the all zero input and measure a specially designated qubit as the outcome. So there's a little bit going on in these last two lines. One of them is the notion of non-negligible that I'm not making too formal. So if you're a computer scientist, a function non-negligible is a function that grows faster than any inverse polynomial. But if you don't want to think about this, think of it as just being like a small number, like 1% or maybe 10%, right? So if this device, if this machine is such that it does completely random things, such that the verifier only has a very small chance of accepting, then there's no guarantee that's required, and there's nothing I could really hope for because the machine is just doing random stuff, and it could be lucky like a very tiny fraction of the time, but even then I'm not going to require that the verifier settles on the correct output of the computation. So I want it to be that the device is accepted at least some fraction of the time, 1%, 10%, and in that case, whenever it's accepted, it should be that the value that's ultimately returned by the verifier has the correct distribution. It's distributed as the outcome of this circuit when I execute it on the zero input. There's a little wiggle here, and this wiggle, you should just interpret it as saying that, well, there's a little bit of a margin of error here. It shouldn't necessarily be exactly the same distribution, but maybe there's 1% or a tenth of a fraction of a percent of wiggle room that's allowed. Yes? Can you do it loud? Because I can't.
Sorry. We do not demand that the probability that D equals 0 when the flag accepts is also equal to the probability that C returns 0 on that input?
Well, they're distributions, so I think it's going to follow. Because conditioned on acceptance, the B has a certain distribution, and I'm just talking at bits. But you're right, yeah, I want both. I want the symmetric condition. Oftentimes, and this might be a simpler setting to think about, we think that the verifier is only interested in a computation that is going to return either 0 or 1 with very high probability, and we just want the outcome of the verifier to be just the 0 or 1, which is whatever the circuit returns with high probability. But I think you can also make the definition in the case where this circuit would be a 50-50 kind of circuit. Okay, so just to make sure we're on the same page, I want to make this, oops, wrong button, very concrete. So here's an example, a very simple circuit that the verifier might want to check. Okay, you start with 0, you apply a Hadamard, you measure, you're going to get 0, 1 with probability 50%, right? And so here's a protocol for checking that circuit. The verifier could go and tell the device, well, look, here's my circuit. Please run the circuit. Then the device would think about it for a certain amount of time, and then it would report an outcome. And it would say, well, look, when I measured, I got a 0. And the question that we're interested in the tutorial is how do we verify this kind of outcome? And you can make this very concrete. So I'm going to try and give you a live demonstration. And I promise that no one from IBM paid me to do that. But if there's someone from IBM there who wants to pay me to do it, then oh, it's not working though. Okay, so you can go online, and I'm sure lots of you have done this already. But IBM is very generous in allowing us to access their quantum device through a website. So you can go to this website there, Quantum Experience, and then you go to Learn Composer, and you can program this 5-qubit machine there. That's the connectivity, that's the 5 qubits, and they tell you what the fidelities and times, and you can select your circuit. So I think the best qubit is like the middle one, the 2, so let's ask IBM to put a Hadamard on this qubit, and then measure. Measure, okay. So you could do a more complicated circuit, but let's just do that circuit, right? And then I click run, and your experiment will be saved, okay? Okay, so it asks you to pay for some credits if you want to actually run it on the machine. So I did this morning, but I don't want to reuse my, I want to see, let's see if my computation from this morning is in the cache. So let's just use the cache. So it just realizes that someone else than me did this computation in the past, right? It's a pretty simple one, but it's not working. Sorry? Oh, I see, okay, yeah, thanks. Oh, it doesn't have it. I did do it this morning, but it doesn't have it. Okay, so it has to look at, well, okay, fine. Let's look at this one from the past. And then, okay, then it tells you the results. So, and here are the results for my circuit. We got 0 probability, just above 0.5, pretty good, right? 2 in 1,000 error, and then this, okay? So it works, right? So, okay, so the question is, you just do this, right? So this is exactly the kind of protocols that I'm talking about. Like you tell the machine to do stuff, time passes, and then it says what it got. So here even, I guess I would run this many times to do the statistics that they're telling me. Oops, this was in case the internet didn't work. I have some backup here, okay, but I did it live. Okay, and so then the question of what can you do, right? How are you going to be able to tell whether it is the correct outcome or not? So before we get into that, let me say something about an approach to this question that I am not going to talk about. And so this is what's generally called benchmarking or randomized benchmarking, where there you think that you have a circuit, so this circuit is a little bit more complicated. And the idea is that you allow yourself what's sometimes referred to as white box instead of black box access to the device. So I imagine that I can look inside of this IBM quantum computer, and I can do things such as saying, well, I'm going to test the Z-gate now. And so how do I test the Z-gate? Well, I ask the device to create a certain family of states at the input of the gate, and then I make a certain family of measurements at the output of the gates, and then I do some statistics, and I do tomography and check that this actually looks like a Z-gate. And I might do that in a bit of a randomized fashion where I also apply random gates on the other wires and check that this doesn't really affect the statistics on the wire that I'm interested in, sort of check that everything is going on fine. So this is a big area of research. It's very important in order to, in practice, benchmark these devices, but it's not what I'm talking about. So there's some very important differences. One major difference that I already referred to is that in order to do benchmarking, you need this white box access to the device. I need to be able to say, look, like you have 5 wires, and let's make certain actions on this wire and that wire, and believe that this is actually what's happening. It also requires me to trust to some extent the preparation of my states and my measurements. I mean, I could also try to benchmark those, but then it's sort of a chicken and egg kind of problem. And another important assumption is that when I do this, I'm assuming that by testing gates and wires individually and observing certain error patterns, then this is going to scale. I'll get a good picture as to what the errors should be if I was to run a much bigger computation that I couldn't do tomography on, because if my number of qubits is too large, then the space is just way too big to do tomography, right? So these are all extra assumptions that I don't want to make. In my scenario, I don't get to look inside the device, and so even though, for example, IBM reported that they have 5 qubits with these connectivities and these times, I don't believe that, or I don't necessarily believe it. And when I say that my circuit should put gates on different wires, that this might not be what is going on, right? I only trust what I see, which is what the feedback the website is giving to me. Okay, and I already mentioned that. So this is one of the main motivations for this black box setting, which is what you could call testing quantum mechanics at scale, or let's say in the high complexity regime. Because if we have the kind of device that I showed you earlier, the 5-qubit computer, that's fine, right? There's nothing to worry about. I can just simulate this machine by hand, pen and paper. 5 qubits is not, I can do the calculation myself. So of course the circuit I ran earlier, it was correct, right? 50-50, I mean, we know that, right? It's the correct answer. But then they have bigger machines. So this is a 16-qubit one. 16-qubit is not that big. I can use a calculator. This one, does anyone know if this exists? So This was announced by, the only information I could find is that at CES, January 2018, so just 1 year ago, Intel said, well, we're creating this 49-qubit quantum device. And then it got picked up by some other news sources, and then no one from Intel here. Okay. So I don't know if this exists or not, but if it did, so 49 qubits, that's I think like a few terabytes. So you could simulate the state of that machine on a pretty large supercomputer, so we're still fine. But the new ones that are maybe coming out sometime soon, such that the Google 70 qubits, so 70 qubits, that's something like 500 or 600 hexabytes. 500 or 600 hexabytes is the estimate. People don't really know. No, it's not the galaxy, it's smaller. It's the total memory size of Google data centers worldwide, like approximately. So in order for Google to simulate the state of its own this own little chip there, it would have to use the amount of space available in its data centers. And these are spread out throughout the world. So in order to do computation, this would be a mess. So things get a little bit tricky, and hopefully soon we'll have bigger computers. And so then the question is that we're really entering a regime that has not been tested, right? We don't actually know for fact that quantum mechanics is going to work fine at these scales. Or maybe the largest size of a coherent quantum computer could be 50 qubits. And if this size limit, if it exists, were between 30 and 40 qubits, I could detect that by doing classical simulations. But if it's between 100 and 200 qubits, then how am I going to tell? Because other than the quantum machine simulating itself or another quantum machine, I don't have a reliable means of making predictions for what the machine is going to say. So that's kind of a question that we're trying to probe by thinking about this verification problem in a very black box, very theoretical way. So before we go on, let me try to motivate my approach, or the approach that I'm taking in this tutorial, a little bit more by connecting the question to others. One of them is pretty much is very similar to what I was just talking about. So there's a lot of talk going on these days about trying to demonstrate the computational advantage that these devices that Google, IBM, Rigetti, others are building these days. There's many proposals that you've heard about, like boson sampling or running random quantum circuits or IQP circuits or all these. And they have one main drawback, which is that they're very hard to verify these things. In general, the complexity of verifying that the quantum computer has performed the correct sampling task scales almost as much as the complexity of actually simulating the task itself on the classical computer. And you're trying to perform tasks that cannot be simulated on the classical computer, yet you'd still want to be able to verify them. And so one question is whether these proposals can be made truly verifiable at scales that go beyond the current limit of like 60 qubits or something. I think some of the ideas that we're going to discuss in the tutorial could be useful to tackle that question, which is an important one because 60 qubits is a moment in time. But hopefully we'll pass that moment, and then we'll still be asking the question. There's a lot of crypto that's going to come into the tutorial, you'll see. So there's ideas such as the idea of performing computation on encrypted data. So you're trying to hide your computation from the device. There's also questions of authentication. So how do you make sure that the device does not mess up with the encryption, with the data that you sent to it? So we'll talk about this a little bit later. The question also connects to the richness of quantum computing in terms of models of computation. So I talked about circuits, but there are other models such as measurement-based quantum computation, or also a model I refer to as the Hamiltonian model of computation that are relevant for verification, and so that we'll get into there. It ties into also to nice question. It brings up some nice questions in fault tolerance because of this asymmetry between the verifier that has a maybe no quantum computer or a very small quantum computer. Then you're asked whether certain interactive protocols can be made fault tolerant when certain nodes in the protocol might not be full quantum computers. Maybe they're just like a single laser or a couple lasers. And so they can't implement any error correcting codes, and so they have errors. And the question is whether the network as a whole can recover from errors into small nodes in the network that themselves can't do fault tolerance because they're just very small nodes. I think that's a question that might be relevant for people who are interested in developing protocols for quantum internet. Okay, there's going to be connections with complexity theory and the power of interactive proofs in complexity theory. And also, of course, some questions in foundations. We'll see a little bit of that. Some of these protocols are based on demonstrations of Bell inequality violations. This is something that works if you can make locality assumptions on your devices. But if you can't, then there's a question of what kind of assumptions or tests or setups could replace Bell inequalities when you don't have access to this locality assumption. I'll talk to that a little bit about that towards the end of the talk. So that's just some general questions that maybe some of you coming at this from different perspectives can think about. Here's the main open question in the area. I just wanted to state it up front and get back to it at the end of the talk, which is whether you can solve the problem that I've been talking about in basically the scenario that I've been describing, where this verifier is a classical computer, just like me running the experiment with IBM and having classical communication with the device. Is verification possible in that scenario? Then we don't know. So I'm going to have to make extra assumptions in order to achieve it, and I'll go over that in a little bit. But every time I make an extra assumption, you can ask yourselves, how would I lift this assumption? And in general, it's going to be an open question, so you can think about it. Okay. So before explaining the different approaches, I'm going to spend a little bit of time trying to be not fully precise, but at least a little more precise than I've been so far in defining the problem so that everyone's on the same page. Are there questions before I do that? Okay, a few slides of definitions. Try to keep it not light enough. So I'll start informal, and then I'll be a little bit more formal. So the informal definition of what we're seeking is what we often refer to as a delegation protocol. And so what we really want to come up is a description for the actions of the verifier, right? So we should be able to say, well, look, verifier, you're interested in this particular quantum circuit, like the one I had earlier or another one. What is it that you're going to tell this device to do in order for you to be able to verify the outcomes that the device reports? So if I was more formal, I'd have to define this in terms of Turing machines. So this verifier is itself a circuit, and how this circuit should be computed by a Turing machine as a function of the input size. The input size here is the size of or an upper bound on the size of the circuit that you want to delegate. I don't want to kill everyone Sunday morning with Turing machines, so I didn't write it. But if you wanted to be more precise, you'd have to go there. At our level, it's going to be fine to think that that's our goal. Our goal is to come up with a protocol, meaning a description of the actions of the verifier. And this verifier gets to interact with a quantum device. As I said, I'll refer to it as the quantum prover. And at the end, it has to return this flag and this bit. And here are three requirements. The first requirement is sort of the basic requirement of that's sometimes I'll call it completeness. For now, let's just call it correctness, which is that sort of if everything goes right, then the verifier should make the right decision. So if the device or the prover implements the computation correctly, if the verifier does everything correctly, then at the end, this verifier should say, well, I'm accepting, and the outcome is B, and B is the correct outcome for the computation. This is like the zeroth order requirement on the protocol. Then the verifiability requirement is now such that whatever the prover does, for any prover, P star, so P star designates a possibly adversarial or faulty prover, one that's outside of my control, but such that it's not completely arbitrary in the sense that my protocol accepts it with non-zero probability, like 1% or something, then I should make the right decision, approximately conditioned on accepting the prover. Right? On those runs when I accept, I will be making the right decision. An extra requirement I haven't talked about right now, but that's going to crop throughout the talk, which is a bit of a side thing, but it's related. It's what's called blindness. So for separate reasons, we might be interested in privacy of our computation. So we might be interested in setting up this protocol so that the prover or the device doesn't actually know what circuit it's running. So we're going to have to hide the circuit in a way that they can do a computation. They don't know exactly what they're computing, but then when we get the outcomes, we can sort of decode them and learn the outcome that we were actually interested in. Okay, so that's the main three requirements: correctness, verifiability, and blindness. So these are informal, and in quantum crypto, you have to be very, is that a question? Yes. Yeah? Oh yeah, I didn't, right, so my notation, because I'm not going to use that notation too much, so but let me explain it. So Vn, V sub n, this is just the verifier. It's the actions of the verifier. It's parameterized by n. N is just a size parameter that says like how big is the circuit. Okay, so you can ignore that. The brackets around C, they're referring to the fact that this circuit is provided as an input to the verifier, so it's just the circuit that's interested in. So that's the Vn of C part. And this here designates informally designates the interaction between the verifier and the prover. And this view symbol there is what does the prover see from the interaction? All the data that the prover gets from the verifier. Okay? And so I'm saying that this view from the prover's point of view should be independent of the circuit that the verifier really cares about. Okay? So anything that the prover gets seeing its way, it should not be able to infer any information about the circuit from that.
So the equation here in our correctness is that interaction between the verifier and the prover returns this.
Yeah, that's what I meant. Yeah, sorry about that. Other questions? Yeah?
Does the prover also return the flag variable?
No.
Except for?
No. The prover doesn't return anything.
Okay.
Yeah. Is that?
Well, no, okay, I was just confused because it looks like that in your definition of correctness.
Oh, I see. Yes, you're right. This is a little bit, my notation is a little bit sloppy. No, what I meant there, yes, it's not the notation, right, it doesn't quite match. What I meant here is that the verifier, in its interaction with the prover, eventually returns this flag and this B. Thanks. Yeah?
Shouldn't it accept some probability, in a correctness condition, shouldn't it accept some probability of spurious rejection?
Yeah, you're right. So the question is, even in the correctness, shouldn't I always sometimes allow to reject? And did I write returns this? Yes. So let's imagine that written here is with high probability, like 0.9. Because you're right, even if this prover performs the right thing, it might, we might want to allow it a little bit of error. Like, for example, the IBM thing didn't say 0.5, right? It said 0.502. I'd still want to accept that, say, okay, like, fair enough, right? I'd want to have a bound on how much I allow, but yeah. So we're going to allow this later. Thanks. The question is, why does the protocol depend on the size of the circuit? It's not very important. It's more of a, if you go in the formal definition with respect to Turing machines, like the reason is just that formally you'd have to specify the actions of this verifier as a circuit, a classical circuit that could be run on my laptop. And a classical circuit has a certain size. And so a given size of verifier is only going to be able to handle certain size of circuits. So I have to fix ahead of time saying, look, I'm only going to be interested in checking circuits that have at most like 1,000 qubits. And then I describe protocols that work for that. If a circuit of 2,000 qubits comes, then I'd have to make myself a little bit bigger to accommodate for that. If you want to think of the same verifier as checking circuits of all sizes, and you're not a complexity theorist, then it's fine. Like it's not something to really worry about. Yeah?
Why are we assuming that the answer for the computation is always 1?
Oh, did I assume that? No, we're not. This question arose earlier already. Let me say the question. The question is, why do I only require this condition in the case that the circuit returns 1? So I'm asking that the probability that this bit is 1 is the same as the probability that the circuit returns 1. What about if the circuit returns 0, right? So it's symmetric. I could put both conditions. So this bit is just 1 or 0. So the probability that the circuit returns 0 is 1 minus the probability that it returns 1. And so this equation implies the same if I flip everything. Yeah?
In this system,
Okay, so I'm not sure I understand the question. Let me reformulate it. So you're saying that in general, B would be a real number and maybe even complex. So no. So here, I'm thinking of B as the outcome of the computation as a classical outcome. So I'm thinking that there's a measurement that's performed at the end, and this measurement is either going to return 0 or 1. So it's always going to be a binary measurement. So in that case, I could still ask your question, which is, well, no, but what if I measure 3 qubits, and then I would get 3-bit outcome? Or maybe I just have a many outcome measurement that returns more than the 0, 1 value, but a few more values. And the question is, well, does the framework extend to that case? The answer is yes. But for simplicity, I'm only considering a situation where I'm interested in running the computation, and then there's a single observable I'm interested in, and this observable should be measured at the end, and it's a binary observable, and then that's what I want to learn. Is that okay? Yeah?
Is there any connection between blindness and the...
Between what?
The blindness situation, the property
Uh-huh.
with the homomorphism encryption?
Oh, so sure, yeah. So the question is there a connection between blindness and something that's referred to as homomorphic encryption? So homomorphic encryption is a way to encrypt your data so that a computer can perform a computation on the data and then report it to you, but without learning the computation. So yes, there's a connection in the sense that homomorphic encryption is a protocol that satisfies the blindness condition. We'll talk about it a little bit later. In general, it doesn't satisfy the verifiability condition, which is the one I'm going to focus on, even though there are some protocols that do satisfy verifiability. I hope I mention that again later when we get to it. Thanks. Okay?
In your previous slide, you put circuit to IBM-Q.
Yeah.
In this sense, there's no blindness, right?
Yes.
Why do you assume here blindness?
Oh, well, okay, so that's another good point. So what you are saying is that when we did the experiment with IBM Experience, the protocol that I designed to run my circuit was not blind because I just told them what the circuit is, right? And this is true. And we're going to see later techniques that would tell me what I would have to send to the IBM machine in order to make it blind so that they don't know what circuit I was running. And so this is a condition that can or can not be satisfied. It's optional. So I can have a protocol that is blind, and I can have a protocol that is not blind. The one that we saw earlier is not blind. We'll see some blind ones later. Thanks. Okay.
From that, I guess the point is, if for verification purpose, it does not need to be blind at all.
Yes, so your remark is that if we're just interested in verification, there is no need to be blind, and that's true. These are distinct conditions, and we don't know of any formal implication between them. Intuitively, they're kind of related. The intuition would be that if a protocol is blind, you could maybe try to put in traps in order to verify the computation. And because the machine doesn't know what computation it's performing, it doesn't know where the traps are. So if it tries to lie, it's also going to lie on the traps, and you might detect that later. But it is very informal. It's the reason why I mentioned blindness, because oftentimes in practice of the theory, people come up with protocols that satisfy both conditions, and so it's relevant to think of them both together. But there are protocols that satisfy the one and not the other in both directions, and we'll see both examples, both types of examples later. So thanks. Okay, so it's good to have questions on the model. Maybe I should move on, but it's important that the model is clear for everyone. I'm going to have one more slide, two more slides of definitions that are a little bit more formal. And if this is a bit too formal for you, I think it's fine to skip the next two slides and stick with the understanding that we have currently. But let me still go over it because, so I was starting to say earlier, in quantum crypto, you have to be very careful with definitions. It's a very tricky field. Sometimes proofs are wrong. And one of the reasons they're wrong is just that, you'd want to say, I wouldn't even have to write that stuff here, right? A protocol is verifiable if the verifier always gives the right answer, and it's blind if the prover doesn't learn anything, right? Who's going to complain with such a definition, right? And then you have a theorem like my protocol is blind, okay. So I have to be very careful. One way in which you have to be careful is that these definitions are what are called like standalone definitions, meaning that they guarantee the properties really in the narrow context of a certain protocol. But if you try to combine things together, things tend to break apart. I want to give you sort of a very toy example of kind of things that could go wrong when using definitions such as these ones. And then I'll give you the real definitions. So here's an example. It's a completely classical example. So things can fail also classically. So let's think about this problem and the protocol for that problem now. It's a bit naive, but so in the classical case, this verifier is given a formula. It's a Boolean formula, like a 3-stat formula, something that looks like this. So there's Boolean variables, x1, x3, x5, and there's a formula, x1 or x negation of x3, etc. And the verifier wants to know if this formula is satisfiable. In general, that's a hard problem, so it's just going to ask the prover about it. And the protocol is like this. The verifier does not send the formula to the prover. It sends nothing. Okay. The prover is supposed to send back an assignment, so n bits, and the verifier is going to check if the assignment satisfies the formula. Okay. That's my protocol. So I claim that this protocol is blind. The reason it's blind, it's a bit stupid, right? I mean, if you're puzzled, it's stupid. But it's blind. I mean, it's obviously blind because the prover got nothing, right? I didn't tell him what the formula is. The prover, I'm just telling him, give me a satisfying assignment. I'm not telling you for what. You send it to me and I check it. So it's blind and verifiable, right? It's blind because the prover there's no information going to the prover. And it's verifiable because, I mean, still I'm checking. What it's not is that it's not correct or complete, because in general, there's no way for even a honest prover to give me the correct assignment because they don't know what I'm interested in, right? But just for the sake of toy example, let's just put that aside and think that this is clearly a blind protocol, right? And it's true. I mean, I'm not lying here. It satisfies my blindness definition, obviously, right? Okay, but now let's imagine that we try to build on this and use this protocol as a building block in another protocol where maybe a similar protocol is repeated multiple times, and so the verifier makes different actions in the future depending on what happened. Well, then kind of a stupid thing that can happen is that a malicious prover might send me back a uniformly random assignment. Okay, I'm going to accept it or not. But suppose that later on in my life, the verifier, depending on whether it accepted or it didn't, performs different actions. For example, if it didn't accept, it just aborts. But if it did accept, if the prover's assignment did work out, then something happens, like I'm going to check the prover on something else, some other computation. Then the prover later is going to learn whether I accepted him in the first round or not. And based on that, it's going to learn what is the probability that this formula accepts a random assignment. So it's going to learn if it's a formula, maybe that's kind of a dummy formula that accepts a lot of random assignments, or it's a harder formula that accepts very few assignments. It's not clear at all if this is useful information, but it learned something about the formula. It learned what is the probability or an estimate on the probability that this formula accepts a random assignment. So it's a very stupid example, but it's just saying that you have to be careful. The definition was fine on its own. If I just do this once and then the world ends, then yes, the prover didn't learn anything about the formula. If the world continues and this verifier and this prover interact together in the future, maybe in a slightly different context, the prover might have more information than I think it has, because it knows maybe that I didn't abort in the first stage. Okay? So in order to deal with this, there's a whole framework in cryptography that's called the ideal world, real world paradigm, so that gives proper definitions of verifiability and blindness that allow you to use protocols as sub-protocols in other larger protocols. Let me just give you a very quick flavor of what these definitions look like. The way it works is that you have to specify what is called the ideal functionality. Like, what's my ideal world picture of what should happen? And here's how it looks like. The ideal world is like this. There's a verifier and there's a computer. But then there's a magic box in the middle. And this box is going to decide like what everyone gets to see. So the verifier puts the circuit it cares about in the box. And the box is fully trusted, right here. So everything that goes on in there is trusted. I'm going to have to allow the box to tell the prover what is the size of the circuit. Because even in any real protocol, the prover is going to learn roughly the size of the circuit that I'm interested in, or an upper bound on it. I mean, I could hide it by making it more complicated, but they'll know that it's not more complicated than whatever they're doing. So I have to allow this. And then the next thing is that the prover is just going to make a choice of behavior that it inputs into the box. So either it's going to say, well, I'll just like run the correct protocol, that's the value 0, or there's two different cheating modes that it could input in the box. And then the box is itself like going to run the computation and determine what gets forwarded to the verifier as a function of the cheating mode that the prover selected. So if the prover decided to do the honest behavior, then the bit B is just the correct value of the circuit on the input 0. And if the prover lied, then two things decided to cheat. Well, two things could happen. The verifier could still get the correct bit because it didn't cheat too much or something like this, or it would get an error. Okay? So the point is that if I had such a magic box that I would trust and that I could put in the middle, then this would exactly implement both verifiable and blind computation. So why is it verifiable? That's pretty easy because whatever the verifier does, what it gets as the output, you can see, is either the correct outcome of the circuit or an error flag. Okay, so it never gets something wrong. This box never says something wrong to the verifier. The worst that could happen is it says an error. So totally fine, right? The verifier only ever gets something correct. And on the prover side, well, nothing comes out except the size of the circuit. So it's blind. The circuit doesn't come out on that side. So if I could implement this thing, I would be done for sure. And so the composable definitions of security, they say, well, you should strive to design a protocol that looks like this from the point of view of any of the two parties separately. So if the verifier interacts with any prover, it looks as if, from its point of view, it was interacting with the ideal box. And same thing for the prover. It looks as if it was interacting with the ideal box. And if you manage to design a protocol that achieves this, then you're really on the right track. Then you can use that protocol as a sub-block into other protocols. This notion of not being able to distinguish the real protocol from the ideal one usually is proven using things that are called simulators that I'm not at all going to get into. I just wanted to tell those of you interested in working with this that these things exist, and be aware that some of the protocols that I'm going to talk about are not known to be secure in this stronger notion of security, only the one in the previous slide, the standalone notion. A lot of them are. So there's a nice paper by Junko, forgot, Portman, Renner, Joe Fitzsimmons, sorry. And so this is a good chance for me to remind those of you who arrived a little bit later that my slides are available on my website. So you just search for my name, and then you go to the top right, and there's a little news blurb, and you click, and there's a PDF there. And all the way at the end is a list of references. So when you see something like this that is not clear what it is at all, at the end, the last slide will say what the paper is, and you can pull it up if you're interested. Okay, so if you're interested in composable security, look at this. For the remainder of the talk, I'm just going to put that aside. I think it's an important issue to be aware of, but for the level of the tutorial, it's not, I'm not going to get into it. Yeah? You have to make it loud, though.
Yeah, it seems to me that here, the thing which is running with the conditions is box,
Yeah.
not the prover. Right?
Yeah.
But then if we need to simulate the box, the thing which simulates is running. So where is security coming from if I have to, is the protocol simulating the box?
Well, no, so maybe you're interested in blindness now, because it's the prover's size we're requiring blindness. And so in order to show that the protocol is blind, I'd have to show that the prover, everything that the prover gets in the real protocol, it could have gotten by interacting with such a box. But what it can get from such a box is nothing more than the size of t. And so if I manage to show that, then I've managed to show that in the real protocol, it wouldn't get any more. And the way we do that is that we design the simulator. The simulator interacts with the box on the prover's side and makes it look like the real protocol. So now the simulator doesn't know the circuit. It only gets t, but still it has to pretend to the prover that it's actually going through the real protocol. And if I manage to do that, then the prover doesn't learn the circuit. No, they only get the size of the circuit. Maybe what I said was confusing you. So again, the statement is that when the real protocol is implemented, so not the one on this slide, like the IBM one, or the real protocol is implemented, and the prover is running it, there should exist another entity that we call the simulator that lies here. So the simulator doesn't know the circuit either. And the prover can't tell if it's having the real interaction, so interacting with the real verifier, or if it's interacting with the simulator. And the simulator itself doesn't know the circuit. It only has access to that here. So the simulator only gets the size, but then it's trying to pretend to the prover that it's running the real protocol. And if such a thing is possible, meaning that the prover doesn't tell whether it's running the protocol with the simulator or the real one, then it wouldn't have been able to learn the circuit because the simulator doesn't know the circuit, because the simulator only has access to this side of the box. I think maybe it'll help later when we see a protocol that actually satisfies its blindness, and then how would such a thing be possible. I mean, I'm not going to prove that anything is secure in this model, but you'll get more intuition once we see protocols. Yeah?
I have a related question. So when you're using the word simulator, does it refer to the box?
No, the simulator is something that attaches itself to the box and tries to pretend. So it attaches itself either here or here, and it tries to pretend either to the verifier or to the prover that they're interacting with the real protocol. Because
Simulating either the verifier or the prover.
yes, but it only has access to the box, not to the. We need the simulator because just like this, of course the verifier can tell the difference between the box and the protocol. The protocol, is going to be more complicated than this, and so they're not, they're just even incomparable objects. So the simulator is just doing like the pretending act. Right. Okay, so before we get to protocols, just one slide to summarize the kind of things, the parameter, like the things that I care about. So we have a size parameter that's going to crop up. I think I'll use n for the number of qubits of the circuit that we want to check. And this means the number of, sorry, oh no, oh my God, okay, sorry. I pressed the wrong button, and so let's get back to it. Yeah, that's just the number of gates of the circuit. And then, okay, so we went over these already, right? So completeness is what I called correctness earlier, probability of accepting a device that just like works as I expect it to work. And this should be 1, or as someone pointed out, like close to 1, not necessarily exactly 1. The soundness is what I refer to as verifiability. Before is just like the security of my protocol. And sorry, PowerPoint messes up the order of my things. So, okay, and then there's 3 complexity parameters that we're interested in. One is what is the complexity of the verifier's actions. I mean, we'd like this verifier to be just like myself, like a laptop, classical, but we might have to relax this a little bit and allow it to itself perform some very simple quantum computations, and we want to keep those to a minimum. Then there's the complexity of the prover, right? If we start hiding this computation, asking it to do more complicated things, that's okay, but we'd like not to, in order to delegate this simple like Hadamard circuit I had before, maybe not have the prover run like a super large circuit just to prove to me that it's running this small one, right? So that's something that we'd like to keep small, that in general we're not so able to. And then the last thing is the interaction. Like, how many rounds of interaction does there have to take? Like, ideally, I'd just send one message, get an answer, decode it, interpret it, and be done. In practice, there's going to be multiple rounds of interaction, and we'd like to keep those to a minimum as well. Okay, so that's the 3 main things that I'm going to care about. Okay, good. We're done with definitions. Let's talk about protocols, and hopefully this slowly helps clarify the definitions also, that I'm a bit more concrete. So the plan is that I'm going to run a little bit quickly over all the different kinds of approaches that we're going to discuss in the tutorial, and then I'll go back and do them one step at a time and explain the main ideas and the new ingredients that are needed to go from one approach to the other, and then this will contrast them and see like some nice new idea at every step along the way. Yeah?
Sorry, for the last slide, are you assuming the prover can't perform some exponential time operation? Like maybe they want to do something really difficult in order to cheat? Are you assuming they can't?
Yeah, that's a good question. This will come in towards the end of the talk. I'll make the assumption. At first, I'm not making it. So I'm really, as I stated earlier, so I'd like my protocol to be correct even if the prover might be some monstrous machine that can do arbitrary computation, like exponential time, any kind of thing. Towards the end, we'll get to the result that's presented tomorrow morning, where you have a protocol that makes a computational assumption on the prover. Yeah.
If you have a circuit that can be divided into like multiple circuits that perform different computations, and then they are all merged together for the final computation, would that help with the blindness?
The question is if my circuit can be split into small chunks such that the final circuit can be executed by running the small chunks independently and then putting things together, would that help achieve blindness? I don't know. Maybe it depends on what you mean a bit more in practice. Not that I know. In general, blindness is like thrown on top of the whole circuit like this. So we'll see very generic ways to achieve the blindness. Other question? Okay, so a little bit of an overview and then more details after the overview. So one of the things that makes this area interesting is, or even that makes quantum computing interesting, is the fact that we have so many different models of quantum computation. And the one I've been talking about so far is just like circuits, and I'm sort of assuming everyone here is familiar with the circuit model. I hope so. Otherwise, take your laptop and Google it, Wikipedia. So there I was thinking that, okay, there's a circuit, and it's a circuit that acts on qubits, and it has certain sets of gates that are specified, and you run the computation. It's a quantum computation. I run it on the input that by default I check is just I assume is just a bunch of zeros, and I'm interested in just the outcome of a measurement. I didn't write the measurements. Well, okay, it got measured here already. So this bit is just like 0, 1. It's a bit, classical bit, and the goal is to determine what is this value, right, or what is its distribution if it's not strongly biased to the one value or the other. Another model of computation that I'm not going to talk about that much in the tutorial because it's different, I'd have to explain it, but it is very relevant, and I'll mention it for certain protocols, is the measurement-based model of computation. So just to give you a very high-level idea of how that works, in that model, there's a fixed state that we call a resource state that looks like this. Sometimes, well, one of them is called cluster state. So it's a state that you can prepare pretty easily by making single qubit rotations and then control z's. But it is just fixed. It just depends on the size of the computation. And then the way you implement a computation on that state is that you measure the qubits one by one in different bases that can be rotated with respect to each other in an adaptive way. So this is fixed. And your computation is going to be specified by a sequence of angles that tell you how to measure the qubits. So you measure the first qubit and the first angle, you get an outcome, and based on that outcome and the instructions for the next qubit, you measure it in a certain basis. You get a new outcome, and based on the new outcome and the instructions for the next qubit, you measure it into. And then you just sweep through the whole thing like this, and at the end, you get an outcome, and the instructions tell you how to interpret that outcome as the actual outcome of the computation. So there's a simple, efficient procedure that can take any circuit, classical can take any circuit, and map it into a set of instructions in this measurement-based model.
The rotation is out on the y-axis.
Yeah, yeah. And you need only, actually depending what your goal is, you need only like a few of these. 8 for sure is enough, I think maybe 4, maybe even less is enough. So just, yeah. Okay, another model that's going to come up later, which is not really a model of computation, but it's useful for verifiability. It's what I'll refer to as the Hamiltonian model. So I'll explain this more later, but this is based on the Kitaev's result that says that given a circuit, you can construct a local Hamiltonian that looks like this. And this local Hamiltonian has the property that the ground state energy, so the smallest eigenvalue of the Hamiltonian, gives you information about the output of the circuit. So if it's a circuit that returns 0 on input 0 with high probability, then this Hamiltonian is going to have pretty low minimum energy. And if the circuit returns 1 with high probability on input 0, then the Hamiltonian is going to have a bit higher minimum energy. So I explain this a little bit later if you've never seen it. If you've seen it, you know what I mean. And so the idea is that we could determine the outcome of a certain computation by determining what is the minimum energy of a local Hamiltonian. that's going to come up later. All right. So there's 4 or 5, I think 5 different models that we're going to be talking about. But in general, just to refresh everyone, this is what we're trying to do, right? So we have the verifier, we have the quantum computer or prover or device that has a quantum computer. The verifier doesn't, but it might have a small one. For example, maybe it has just like a single qubit computer. And the two of them are going to interact. Some of this interaction is going to be classical interaction, some of it is going to be quantum interaction. And the challenge is to set up this interaction so that the verifier can verify the computation that's being performed by the device while minimizing resources at the verifier, right? So the most naive thing would be verifier actually has a quantum computer that they trust, so everything the verifier has they trust, then they just do it, and then that's it, right? What if they have less than a full-blown computer or less than the computer that allows them to run the circuit that they care about? Then, okay, how do we set this up? And the main question that I want you to have in mind, and this is the main challenge in analyzing protocols in the black box setting that's differentiated from benchmarking, which is that I drew qubits here, right? But when you model this, when you do a security analysis, you don't know for a fact that there's qubits there, right? When I interacted with the IBM thing, I don't know for a fact that there's 5 qubits. So when I say things like, please execute an H gate or a Z gate, this is just like talk, right? But in fact, I don't know if the machine is just like simulating something classical or if it actually has 5 qubits that I can address individually. And so it's very difficult if you make the verifier completely classical to say, how do I get a handle on the computation that's happening there that's supposed to be this like huge quantum computation that if I were to simulate it would be exponentially complex, and how do I know what's going on inside this machine, right? So how do I get a handle on the qubits that this machine is supposed to be operating on, given that I don't have any direct access to them? Okay? So all the time you can ask yourself this question and see what the answer is. And each of the types of protocols that I'm going to introduce has its own way of giving a handle for the verifier to get this control on the qubits. Okay, so the first model that's actually not verifiable, but it's the first reference in this area. So this is a paper by Childs from, I think, 2001 or 2, but then it got published a little later, where he introduced the model of blind delegation. And in his model, the verifier has a constant size quantum computer, so just a few qubits. And on top of that, it can only perform very simple kinds of gates, like Pauli sigma x, sigma z, sigma y gates. That's it. And so the verifier is going to have many rounds interaction with the device, exchanging quantum qubits. And you'll get a protocol that's blind but not verifiable. I'll explain this protocol later. The idea basically is that the machine is serving as a big quantum memory for you. Okay, and there in this model, the question of where are the qubits doesn't directly apply because we're not talking about verifiability, we're only talking about blindness. So we're actually assuming that the device does the right thing, and the only thing that we're worried about is what information do they learn. So there the question is a bit moot. I mean, I put it there, but it's not. Okay, so the first, as far as I know, protocols for verifiable delegation of computation came in 2008, 2 independent works by Aronov, Benoit, and Eban, and then the other work by Broadbent, Fitzsimmons, and Kashefi. And they're in a model that's called the prepare and send model. So in that model, again, the verifier has a small constant-sized quantum computer. But the only thing that it can do is it can initialize qubits in this computer and then ship them to the prover. Then the prover is supposed to run the computation, and there's going to be a little bit of interaction to check that things are going on well. But this interaction will be classical. So the only quantum interaction is from the verifier to the prover. And the 2 papers, they use different models. So the first one uses the circuit model. And the way they achieve verifiability is by using authentication codes that I'll explain. And the other is in the measurement-based model, and it achieves verifiability using the idea of traps that I'll just mention but not go into later. And so in that case, if you ask the question, where are the qubits? Well, the verifier prepares them. So this is how they get a handle on the space of the prover. You can think of these protocols as, at least for in the circuit model, as preparing the qubit. putting it in a big, I mean not big, like in a quantum lockbox that has a little code and authentication code, and then shipping the lockbox to the device so that the device can operate on the locked qubits, but it can't tell what they are, and if it tries to not do the right operation, this is going to be detected by the classical interaction that takes place later. So I'm going to explain all of this in some amount of detail a little later. Okay, second model. This is the first work that gave a verifiable delegation protocol with a purely classical verifier. But they had to change the model for the prover and assume that this prover device is, in fact, can be split in two, and you can do bell tests. So there's two computers that are spatially isolated, and you can do bell tests between it. And that is going to give you a leverage on the qubits of the devices. So I'll also explain that a little bit later. So I don't want to say too much about it now, but this is where the qubits come from in that model. The bell tests, through a property known as rigidity or self-testing, are going to guarantee that these provers must share EPR pairs, and once you have EPR pairs, you have qubits, and you're going to be able to use that to drive your computation in a way that's verifiable. Okay, so now in the other direction, we had prepare and send protocols. Now we have receive and measure protocols. So these were introduced in these works by Morimae and Fuji, and Morimae and Fitzsimmons. I think the first work is Morimae and Fuji from 2013. There, the idea is that the verifier also, again, has a small quantum computer, but what they can do with it is make measurements. So I'm going to ask the prover to set up the computation and then send me one qubit at a time to the verifier, and the verifier is just going to measure these single qubits. And at the end of the protocol, make measurements, and based on that, decide on the outcome of the verification. So again, there's there's a lot of works, but there's two main lines of works that in this model. Some of them in the measurement-based model, where the prover is going to prepare this resource state and send it one qubit at a time, and then the verifier is going to sort of do this adaptive computation that I described earlier. And the others are in the Hamiltonian model, and I'll describe those in the Hamiltonian model a little bit more when we get to it. And here, where are the qubits? The verifier sees them, measures them, and so this is how we get a handle on the qubits. Okay, last model. In all the previous models, the verifier had a bit of a quantum computer, and now we get to your question, or the question that was over there. What about a purely classical verifier? And so there's a recent paper that does this, that's presented tomorrow morning by Urmila Mahadev. And I call this commit and reveal protocol. So the idea is that now the verifier is going to be completely classical. The protocol is going to have a little bit the same flavor as the ones on the previous slide, where the prover is going to be required to set up the computation and then send the qubits one at a time. Except if the verifier is not quantum, it can't receive qubits. So instead, I'll have a little protocol by which the prover is going to commit to these qubits, so send me classical information that proves to me that it created the qubit, and later some more classical information that reveals to me the outcomes of measurements on those qubits. So I'll explain this when we get to it. And here there's an extra assumption. So we got rid of the quantum on the side of the verifier, but the assumption is the one that was brought up earlier. For soundness of that protocol, I'll have to assume that this prover is not too powerful. So it can implement arbitrary polynomial size quantum computation, but not more. Very specifically, I'll have to make the assumption that it can't break a post-quantum cryptographic scheme that's based on the learning of errors problem that we believe quantum computers cannot break, but then that's just a belief, right? So it's an extra assumption that we'll make in order to get rid of anything quantum at the verifier. So that's a protocol I could run with IBM if they had a bit more than 5 qubits. Okay, so we'll get to it at the end. And in that case, the where are the qubits question is a bit more subtle, and I'll try to describe that to you, because the verifier has no quantum ability, so how does it know that this prover actually has qubits and run a computation on them? And this is going to come from the crypto. Okay, so this was fast, but then you can forget everything anyways. We're going to get into it into more detail. So here's the roadmap for the next half-hour break, hour and a half. So I'm going to describe protocols in, I hope, fairly concrete way, and at the same time explain the interesting ideas so that you can use them in different contexts. So we'll start with the easier kind of protocols where there's quantum interaction and the verifier has a quantum computer. And this is the protocol that was only blind. And then I'll tell you about quantum encryption and authentication in order to get the prepare and send, protocols. And then I'll tell you a little bit about self-testing and how we get these two-prover protocols. And then we'll go into the bottom line, which is starting from the prepare and measure protocols. I'll explain the ideas that go into that, so that will involve describing this Hamiltonian model in a little bit more detail. And from there, you can again use the self-testing ideas to get two-prover protocols. So there's two different kinds of two-prover protocols that come from the top row or the bottom row. Or you can use the crypto that I just mentioned in order to get the classical protocol. Okay? So each arrow is a new idea. And I want to explain these ideas and how they help us make progress. Even though it looks like things are flowing from the left to the right on the picture, none of the results, there's 5 results there, or 5 series of results, none of them is stronger strictly than another. You're always moving right, you always gain something. The verifier is a bit simpler, but you also lose something. For example, here you have to make an extra assumption, here you have to make an extra assumption. Also, the protocols tend to get more complicated. Sometimes maybe you lose blindness. There's always something to gain, something to lose. And that's why I think it's instructive to go over everything, because all of them have ideas that, even though there's a later paper that does something different, these ideas are still interesting for themselves. Okay, we're going to get to it in just a moment, but I wanted to have just one slide on experiments. So I apologize for the experimentalists in the audience. I hope they're here, though, because I hope you can follow. But this is very interesting from an experimental point of view. Okay, can you implement any of these things? And there has been experiments. Maybe it would be more useful to give that slide later, but I wanted to say it now so that it's you realize this is not only theory land. So there's 3 main experiments that I'm aware of, but I might not know of the latest ones. So the first one that I know is by a group from, I think, University of Vienna. So this is Stephanie Bars and co-authors. They implemented protocols in the prepare and send model. So this is using photonics. I think they have 4 lasers. The verifier beams these 4 photons one at a time to the prover, and then the prover, using some optics, implements the computation. There's a somewhat similar, in the sense that it's also based on photonics experiments from later, also from University of Vienna, that's now in the prepare and measure model. I put the picture there. I don't fully understand it, but we can look at it. This is what's happening at the server. So they have 4 lasers or something, and then various mirrors. And so this is preparing the cluster state, 4-qubit cluster state. And then it's beaming the qubits of this. So it has to do these rotations and control Z's that I mentioned earlier. And then it's beaming the qubits one by one to Alice. And then Alice, I'm not sure why she has 4 detectors. She should have only 1, but okay. So, and then she's implementing the computation by just making a measurement. She gets a photon, she measures it, and then she makes an adaptive measurement, maybe because these measurements have to be adaptive. They make an adaptive measurement on the next one, etc. And at the end, she learns the outcome of the computation. And so they run this many times, and some of the runs, the kind of things that Alice does is checking that Bob has prepared the right cluster state. And some of the runs are implementing a 1-gate. Actually, they also have some 2-qubit gates that you can implement on the 4-qubit cluster state. So they only can check 1 gate at a time, but they did test a universal set of gates in that way. And then the last experiment, this was correct. Last experiment that I know of is in the two-prover model. So this is by a group from Zhan Wei Pan's group in China from a couple years ago. So they implemented this, again, using photons. So I think I have a picture. So it looks like this. So there's 3, they have 3 pairs of lasers that create, so 3 PR pairs. So these 4 things, there are 4 distinct experiments. There's experiments with different setups. And so they create 3 PR pairs, and then they do bell tests, like thousands of bell tests, in order to get good enough statistics. And then randomly, some of these bell tests, they use to test a specific gate, like a Hadamard gate or a CNOT gate or something like this. And in the paper, they say that they use that to delegate Shor's algorithm for factoring 15. I'm not exactly sure how the circuit fits in 3 qubits. I think what they did is they basically broke down Shor's algorithm for factoring 15 qubits to like a single qubit circuit, a single gate, and then they tested the gate in the model. So they also cut some corners in terms of the, exactly the verifiability. You assume that these runs are independent and things like this, so the theoretical proofs don't quite apply. Still, I think it's a major achievement to be able to do this. Like, there's thousands or tens of thousands of bell tests that were run in just like a few days maybe or something. So that's the experiments that I know of, and I hope that there's more coming soon. Okay, so we're going to get started on the real stuff. Anyone have something on their mind that they want to share? We have like 20 minutes to the break, so I want to keep going for 20 more minutes.
The three examples you gave here all use the photon-based approach. It just
Yeah, so maybe someone in the audience knows. So, so what you're pointing out is that the three examples, I think, were based on photonics. I don't know of any example. So you could imagine creating these protocols based on ion traps and maybe beaming photons at the ion trap, and it would allow you to do a more complex computation because the ion trap can hold more photons than just the photons that you have to do it immediately. I don't know if there's been any such experiment. I don't know if anyone here knows. Joe, yeah. Can you speak a little louder?
There's one experiment you missed from Mars in 13 that was verification using the same 4-photon cluster state. But other than that, everything, ultimately together, it's all being photon.
Okay.
It's hard because there's not really a way to get photons in or out.
To get what?
There's not really a way to connect two devices, or that's only like very recently been
Yeah, yeah, yeah.
Ion traps seem ideal, but it's not
Okay. Okay, so what Joe is saying is that I did miss an experiment, so I wasn't exhaustive, but it's also based on photonics. You said that superconducting devices, then it's a bit challenging because we don't know how to connect them. So even just if the verifier needs even just a single qubit and be able to interact using that single qubit with the superconducting device, it's not clear how to do that. Ion traps, we know how to do that, so have multiple ion traps interact using photons, but the experiment hasn't been realized or publicized yet, but I think it should come, yeah.
In principle, there's many technologies that do the job. Photonic approaches are cheaper. I think that's what's driving it, is budget concerns.
Well, this was some Janway span group, right? I mean, they don't these guys do satellites and stuff, right? So, I'm joking.
On a refrigerator versus the cost of an optical bag.
Yeah. No, but you're right. Yeah, yeah.
Funding agency will question.
Yeah, I was joking. You're right. You're right. I mean, they are costly experiments. Okay, so let's get to it. Okay. Yeah.
Going back a little bit,
Okay.
you said one of the applications or uses of the verification techniques is for the near-term demonstration of quantum advantage. So it's not clear to me what exactly verification will do. Will it prove that the demonstration is quantum, or will it also prove that some other simulation is moving quantum things are stronger than classical?
Oh, no. So the question is if we use these ideas from verification towards the goal of near-term quantum, demonstrating near-term quantum advantage, then what would it achieve exactly? What would it prove? And so the fact that the task that we're considering is hard for a classical device and easy for a quantum one, this is known already under complexity theoretic assumptions. So it's not going to make a difference at that level. At the level at which it could make a difference is that it could allow you to verify that the quantum device has implemented the correct sampling task. Currently, you can do it and you can do statistics, but there's not a very sound basis for the fact that if you see these statistics up to a certain precision, then it's not clear exactly how much you've demonstrated. I mean, there's a lot of work in that area, and I don't want to get into it. I mean, we'll hear about it, I'm sure, also at QIP. So it would help just in the verification. Of course, this is not a solved problem at all. So what I'm going to say is does not currently help because the overheads are too large, and so you end up having something that you cannot run on the near-term device. And so I'm just saying the ideas might be helpful, but currently it's not. It's an open question. Okay, good. So let's get to it. So I want to start by the most basic, but also the most fundamental ideas in this area, which are just encryption, computing on encrypted data, authentication, computing on data that's encrypted and authenticated. So our starting point is the protocol by Childs from 2005. And I'm going to describe that protocol a little bit in slightly more detail. So remember that the verifier has a quantum circuit that's just specified as a list of gates, and it wants to determine what is the outcome of that circuit on input 0. But in this model, the verifier doesn't have a full-blown quantum computer. It just has a few, maybe just a couple qubits, and it can do sigma x, sigma z, sigma y gates on these qubits, but that's it, right? So it's going to delegate the computation to the device in a way that's blind but not verifiable. We'll get to verifiability later. For now, let's focus on blindness. One small trick that I'm going to employ throughout the talk is that you can think of the verifier as being interested in the circuit, or you can think of it as being interested in the input to the circuit. This is just a trick. I can think of the device as running a universal, what's known as a universal circuit. And the universal circuit is like a fixed big circuit. It's just like everyone knows it. It doesn't depend on anything. And you put it as input, a description of any other circuit, and then it's just going to simulate it and give you the outcome. Okay? So this means that the device already knows what circuit it's supposed to run. It's this universal circuit. But it doesn't yet know the input of that circuit, where the input is going to be a specification of the actual circuit that the verifier cares about. Okay? So it's just like switching how we think about things. So what we're interested in now is hiding the input to the universal circuit, yes?
On C0, are we talking about n number of...
No, it's again as before, sorry, yeah, no. By obtain C0, good question. No, I mean, I always think of C as at the end measuring one qubit and getting a bit as outcome. And this is my shorthand for just this one bit that was called B earlier, yeah.
So the circuit size is always just one wire?
The circuit output is one wire. So the other, there's many more wires, but the others, they're just traced out at the end of the computation. And so the technique that we'll use is this idea of computing on encrypted data. So the verifier is going to encrypt this input and send it to the device so that the device can run the computation without learning what input it's operating on. And the computation has been fixed. It's this universal circuit. Okay, so I'm going to explain how this is done. The main idea is the quantum one-time pad. I think lots of people have seen the quantum one-time pad, but maybe not everyone. So let me go over it also because we'll use it later. So this is how you hide a quantum state. So let's just take a single qubit state, psi. And I'm going to apply to psi a random z and a random x. So I select two random bits, a and b, and I apply z if b was 1, and x if a was 1. So there's 4 possible options. Z is just a phase flip, and x is a bit flip. So to be very concrete, this is what happens. My qubit in general is something like this. This is something the verifier is going to do. And if b is 1, I do a phase flip, so I flip the phase. And if a is 1, I do a bit flip. So this is between the top 2 rows and the bottom 2 rows. Okay, so depending on my choices here, the qubit could be mapped to any of these 4 qubits. And the important property of this operation is that to a party, such as the device, that does not know what operation was applied, the resulting qubit looks like a totally mixed state. No information at all transpired. The reason is just if you average over all 4 possibilities of what happens when you apply nothing, or just x, or just z, or both x and z to that qubit, you do the computation, and it's a one-line computation. You have it here. Cross terms cancel out, and you just get the totally mixed state. Okay. On the other hand, someone who does know what x and z are, what a and b are, can perform the encryption. This is like a single qubit computation, only applies x and z gates, and can also do it in reverse, right? If I apply again x and z, I'm going to recover the original qubit. So that's the idea for quantum encryption. You need 2 bits, classical bits, per qubit that you want to encrypt. If psi was more than 1 qubit, you do this independently for all the qubits. So this is what we're going to do. We're going to take our input, which is a specification of the circuit that we want to run, but it's a classical input. We're going to encode it in a quantum state, and then we're going to apply the one-time pad to that quantum state, ship it to the device, 1 qubit at a time. Now, the device has all the qubits, and I wanted to run a computation. So the question is, how can you run this computation when you don't know what you're running it on, right? And so there's some things that are easy and some things that are harder. So things that are easy are Clifford gates. So Clifford gates, by definition, are the ones that stabilize Paulis. So don't quite commute with the Paulis, but transform them in a way that's known. So examples of Clifford gates are X and Z themselves. Also, the Hadamard gate is a Clifford gate. The C0 gate is a Clifford gate. So let's just do one example, Hadamard gate. So let's say we actually want to apply a Hadamard gate on the qubit. But we don't have the qubit. We have the encrypted version that has this X and Z that we don't know what they are. Okay, well, let's just apply the Hadamard gate on top of it, right? By using the, not commutation, but I don't know how they're called, like the way H interacts with X and Z, you can flip it past the X and it'll become a Z, Z to the B. Or did I, Z to the A, I'm sorry, this is what I have there. And you can flip it past the X, and you'll get, the H gets there, and these, the A and B got exchanged, and I forgot the phase, right? There should be a phase -1 to the A times B. That's a global phase, we don't care about it. Okay, so applying an H on the outside is the same as applying an H on the inside, provided you remember to switch these two quantities A and B, which is something that the device can't do because they don't know what A and B are, but the verifier can. The verifier knows what A and B are. Okay, so these kinds of gates, they can just be applied directly on top of the encryption, and the effect is that they change what the encryption is, but it's something the verifier can keep track classically. There was a question?
I was just wondering, is that true for an arbitrary psi or only for an encrypted?
That's true for an arbitrary psi. So psi is, in this line, psi is an arbitrary single qubit state. It would be fine if it was many qubits and I was operating on only the H wasn't just one of them. And yeah, it works for any psi. The encryption, the fact that psi is encrypted is the fact that I applied to the X and Z there. So this is a calculation, right? It's just that HX equals ZH, and etc. H conjugates X to Z, I should say, more properly. Okay, so Clifford gates are easy, but Clifford gates are not universal, so we need one more gate. So here's an example of a gate that lets us do universal circuits. It's the T gate. Sometimes it's called pi by 8, where you put like minus pi by 8 and pi by 8, but I just call it T and write it like this. Another gate that's going to be relevant in just a second is the phase gate. That's the square of the T gate, and it's that. So in order to implement any circuit, I need to do my Clifford gates, H, C0, but also the T gate. And the T gate is a bit of a problem because it's not a Clifford gate, so it doesn't have such a nice relation with the one-time pad. So what's going to happen if you do the computation, I didn't do the full computation, but something like this is going to happen. So you apply it on the outside, and applying it on the outside, again, this is true for any psi. I mean, this is actually a relation on the operators. It doesn't depend on the state. Applying it on the outside is equivalent to applying it on the inside, which is what you want, because this is where you want the computation to happen. Changing the keys, so I didn't say what's A prime and B prime. They're just some well-known function of A and B, like the sum or something like this. I just didn't write what it is. But there might be a P gate here that's not an X or a Z in order for the equation to be correct, right? So depending on the value of A and B, there's a C, and there might be a P gate, okay? So if I don't put the P, the equation is just wrong. If I could get away without the P, I'd be done. Okay, but I'm not, there's a P. I didn't want a P there. My circuit had a T, not a P. I need to get rid of that. Okay, how do you get rid of the P? Well, P gate is a Clifford gate, so we're going to be able to use the tricks from before. And so there is going to be a C prime that depends on all the things that you computed before, such that if you apply a P on the outside, then it's going to cancel the P on the inside. And you get at what you wanted, updated the keys. The tricky thing there is that in order to, so you applied the T on the outside, right? It went inside, but there might be a P. If there is a P, you might need to get rid of. To get rid of it, it's okay. You just apply a P on the outside, and it'll get rid of it. The question is, did you need to do this or not? In order to figure out whether you needed to do it or not, you need to know what A and B are. So this is something the verifier knows, but not the quantum computer. So here the quantum computer could do it, and then that's it. There was no information needed from the verifier. Here, the quantum computer can do it, but then it needs to ask the verifier, should I apply a P correction or not? Remember that here we're thinking about the prover being honest, right? It really wants to do the thing, but it just doesn't know. The computation is encrypted, and so it needs to know whether it should apply this correction, and in order to know it, it needs to ask the verifier, should I do it or not? And the verifier who has the keys is going to say, yeah, you should do it or not. You'd have to worry if like telling the device, oh, should you do the correction or not, might reveal information. If you set it up properly, it doesn't. So this is not obvious from the slide, but it's you know. Such a like slightly messy thing is necessary because those of you who are familiar with recent theorem says that no error correcting code. It's not clear that error correcting code here is relevant, but this is how we're hiding the information. Allows you to do transversal application of universal gate set. I'm actually not going to explain what this means. It's just basically saying that we need such a slightly more complicated thing. So that's basically the protocol. So throughout the remainder of the talk, I'm going to sort of sometimes like describe ideas behind the protocol like this. And then I'm going to have a running example that's always going to be the same. And I want it to be a little bit concrete because it's a tutorial. So I'm just going to like explain how do you run this circuit in a blind way using the ideas in the previous slide, just like so that you have something that you can hang on to. I mean, I won't do the whole circuit because it'd be too long, but I'll do the start of it. Okay? So I hope that's useful. So just to connect the dots. So this is the circuit. It has an H gate, T gate that we had on previous slide, other H gate measure. I don't even know what it returns. It doesn't matter because the quantum computer is going to do it for us. And the first thing is to encrypt my input. So I'm going to encrypt the input like this using a pair of random bits. And again, okay, maybe switch your minds. Think that this is the universal circuit, and the input I really care is the 0. Okay, I mean, could it be the 1? Okay, so I hide my input using the one-time pad, and I send it to the device. The device just doesn't, this is no information at all. It sees a totally mixed state. Okay, and then it has to run the circuit, and it knows what the circuit is. It's a universal circuit. First gate is H gate. Okay, H gate is easy. Let's just apply it on top of it. And in Child's protocol, the server applies the gate and then sends back the qubit on which it applied the gate to the verifier. But in the case of a Clifford gate, the verifier is going to observe what we observed in the previous slide, which is that this H gate commutes in a predictable way with the encryption. And the only thing is that it's going to re-encrypt. So it'll use its single qubit Pauli gate computer to re-encrypt and ship it back to the, this re-encryption is going to be useful later, not right now. Ship it back to the computer. This is easy, but then later comes a non-Clifford gate, like a T gate, and the device is again going to apply it on the outside and ship back the result to the verifier, only just on this one qubit that it acted on. The verifier is going to observe what we observed in the previous slide, which is, so this is no quantum computation, right? It just knows that this equation, this is math, it just knows that this holds for values A prime, B prime that it knew, and A double prime, B double prime, and C that it can compute. And so based on that, it knows whether the P should be applied or not. Now, because they're starting to get a little bit of correlations between this C and this A double prime and B double prime, for security, it's just going to, again, like re-encrypt everything using different keys and send back, so this should be A double prime and B triple prime, the thing, and it's going to tell the device whether it should apply this P correction or not. And then the device is just going to do what it's told, and then we're going to run the whole circuit like this, right? So I teach, yeah. Can you speak a little louder?
The part where you have the Clifford moving past the XA and the ZB.
Yeah.
You have an XB and a ZA. Is it intended that the XB and the ZA should be an XA and ZB?
Sorry, which part? Is it correct, or? There might be a typo. I know at some point I had a typo on this slide, and I think I corrected it, but is it okay?
It should be ZAXB.
So where? Because there's a lot of stuff going on. Oh yeah, so I forgot the global phases. That's one thing for sure. Yeah, I forgot the phases. We can ignore them because it's a global phase, but yeah, thanks. So, yeah. We're gonna break just, let's just break right now. So, well, let me just summarize. So that's a protocol. So we only need single qubit exchanges because the qubits, this circuit might have 2 qubit gates. Okay, so in that case, we'd need like 2 qubits to be sent, but no more than 2 qubits at a time. The qubits that are not acted on, they're just not acted on. The device uses as a big memory. When there's a gate to be applied, the device applies it on top of the encryption, And in the good cases, it just commutes with it, nothing to be done. In the harder cases, like a T, you need to ship it back to the verifier so that it can do this like re-encryption thing, which is very easy, just manipulations of Pauli's. Using a classical computer, and its knowledge of the keys, it checks whether a correction needs to be done or not. And if it does, it tells the device to do the correction and then continue. So this is the protocol using which we could implement delegate blindly, but it's not verifiable. There's no point in this protocol where I'm checking that the device does the right gates. If instead of a Hadamard, it applied the sigma z or a phase gate, or when I ask it to apply the phase gate, it doesn't, I don't know. I'm not checking that, right? So it's blind but not verifiable. In order to make it verifiable, we're going to add one layer to this one-time pad, to the encryption, which is called authentication. So I'm going to not only encrypt the qubits, but also authenticate them in a way that if you don't apply the right gate, I'm going to be able to detect the application of the gate that was not intended. But I think it'd be good to take a break now, and so I'll explain that after the break.